9.5 example 4. In this example, we're going to look at proving that the alternating harmonic series is convergent, that it's not absolutely convergent, and we're going to find a bound for the truncation error after 99 terms. So there are three things we're going to show today: that it is convergent, but it's not absolutely convergent, and the bound for the 99th term. So the first thing we need to do is talk about what is the alternating harmonic series. Well, the alternating harmonic series is just the harmonic series, 1 over n, and we need it to alternate, so it's -1 to the n plus 1. So this is the alternating harmonic series. So the first thing we need to do is show that this thing converges. So I'm going to write this as a series, and I get n equals 1 to infinity, -1 to the n plus 1 over n. So that means that a sub n is equal to 1 over n, which is everything except the -1 part. So according to the alternating series test, we need three things. The first thing is it needs to be decreasing, it needs to be positive, and the limit has to go to 0. So 1 over n definitely decreases, because if I write this out, it's 1 plus 1/2 plus 1/3 plus 1/4 plus ... And that's definitely going to go ahead and decrease. And we know that the first term is bigger than the second term, which is bigger than the third term. It's positive. All of those numbers are positive. And we need to show the limit. So the limit as n approaches infinity of a sub n, which is the limit as n approaches infinity of 1 over n, will give me 0. So therefore, n equals 1 to infinity of -1 to the n plus 1 over n converges by the alternating series test. Okay, now we need to test absolute convergence. And this is something we haven't had to do before when working with the ratio test, because the ratio test implies absolute convergence because you're putting on absolute value bars. So what we're going to do now is we're going to look at our series, and we're going to throw absolute value bars on it, because now we're testing for absolute convergence. Basically, throw absolute values, you test for absolute convergence. Well, this ends up equaling the series from 1 to infinity of just 1 over n, and we know that this diverges. And why does this diverge? Because 1 over n is the harmonic series. And we can also test that with a p-series test, right? Because the power right here is 1, and for it to converge, it needs to be larger than 1. So therefore, we say not absolutely convergent. In part C, we're going to find the error. So we want to find the error after the 99th term. So all we have to do is plug in the 100th term. So the error at the 99th term, we're going to use n equals 100. We used the term past the term we want. So we go, this is going to be u sub 100, which is going to be 1 over 100. All I'm doing is plugging in the n for the n values in my series, ignoring the alternating series part. And then to determine if it's positive or negative, all I do is look at the 99th term. So u sub 99 is going to be -1 to the 1 plus 99 over 1 over 99. So this is -1 to the 100 over 99, which is positive. So I know this number is going to be positive. And that's it. So the error in this is going to be 0.01. And the error talks about if it's going to be plus or minus in a certain direction. So after summing everything up to 99 numbers, we will be within 1/100th of the correct summation. Because the alternating harmonic series is convergent, but not absolutely convergent, we call it conditionally convergent. On your own, I want you to determine whether the series converges absolutely or conditionally, or it diverges. Then I want you to find a bound for the truncation error after the 99th term. So go ahead, pause the video, and try that now. Okay, so let's give it a shot. So the first thing I'm going to do is check the conditions for the alternating series test. So the first thing I check is it decreasing? Yes, because n squared grows faster than 1 plus n. Is it continuous? Yes, it's going to be continuous because 1 plus n over n squared is continuous except at 0. However, we're starting at 1. And is it positive? Yes, I'm not going to get any negative terms. So we're all set. We can go ahead and use our alternating series test. So the alternating series test is the limit as n approaches infinity of a sub n. So it's the limit as n approaches infinity of 1 plus n over n squared. And using an n behavior model, we get that this is the limit as n approaches infinity of n over n squared, which is the limit as n approaches infinity of 1 over n, which equals 0. So therefore, it's going to converge by the alternating series test. But we don't know if it's absolutely convergent or just conditionally convergent. And so we got to figure that out. So when we get equals 0, it implies that it conditionally converges. So now we're going to check the absolute convergence part. So we're going to write down our series, which is n equals 1 to infinity of negative 1 to the n plus 1, 1 plus n, all divided by n squared. And we're going to throw some absolute values bars around it. Now all that does is get rid of the negative term. So now this is the series from n equals 1 to infinity, 1 plus n over n squared. Well, I can use a limit comparison test on that. And I'm going to compare it to the series of n equals 1 to infinity of n over n squared, which is the series from 1 to infinity of 1 over n. And I know that this is going to diverge. So I'm going to go ahead and use the limit comparison test to find out if this diverges. So after taking that limit, I go ahead and get that it equals 1 using an n behavior model and setting the limit to infinity. Well, I know 1 is greater than 0, so using the limit comparison test, I can see that they both behave the same way. So the limit comparison test tells me that this series will diverge. So when I used the alternating series test, it converged. When I did the absolute, it diverged, which means that my series is only going to converge conditionally. So the series from n equals 1 to infinity of negative 1 to the n plus 1 times n plus 1 over n squared only converges conditionally because when I did the absolute value, it diverged by the limit comparison test. Now we need to find the truncation error. So I go ahead and I find u of 99, which means I'm just plugging in 99. So negative 1 to the 100 times 100 over 99 squared. I don't really care what this number is. I only care that it's positive, which tells me my 100th term is also going to be positive. So it's just, I just plug in the number. So it's 101 over 100 squared, which equals 0.0101. And we call this the truncation error.